All right. Oh, thank you. I'm doing well. I mean, it's Monday and um, and we have a midterm this week. You know, I feel like I have more stress. I don't expect any sympathy from you because you guys you have to take the exams. But I was talking to my dad the other day, and he says he still has this recurring dream. He's like 70, and he says, he still has this recurring dream where he's back in college and he wakes up and it's like the day of the final exam and he didn't study or prepare for it and and then he wakes up and he's like, why did I have this dream? I'm 70 years old, I'm not in college. I don't know if you guys ever had that dream. So I never had that dream where I was unprepared for an exam, but I feel like that's a common dream that people have where they wake up, they have this nightmare where they're unprepared for an exam. I've never had that dream. But after I started teaching, I've had like the opposite dream where it's the day of an exam and I forgot to make photocopies of the exam. And like I'm supposed to pass out exams to the class, but like the photocopies aren't ready and I don't know what to do. Like, and so um, so yeah, I never had the dream where I was unprepared for the exam, but I've had dreams where I'm unprepared to give the exam. And so anyway, um, so I always feel a lot of stress when it comes to giving the exam. So I have to get just kind of make sure everything's ready to go for Wednesday. But again, I'm not expecting much sympathy from you guys because you guys are the ones who actually have to take the exam and stuff. So that's fine. It's part of the schooling experience, giving and taking exams, and that's I wish there was like a better way to evaluate learning, but the only other way I can think it'd be just very time consuming where I'd just like sit down and we'd have a chat and you tell me everything you learned in the class. That's probably like even more nerve-wracking for you if you know it's going to be like you're going to be evaluated on that. So but I think I would enjoy it where we just have a chat, but if it was like in an informal, I don't know. Okay. Well, anyway, today I want to show you how our simple neural network would work for a kind of a cool setting. And in this case, we're going to look at the MNIST handwriting handwriting digit database. Have you guys heard of this? The MNIST database? Some of you have heard of it. Some of you haven't. Okay. So is um, this was really when like I would say this is one of the most favorite data sets just because it was so much effort was put into making this data set into being very clean and easily used, right? And basically, um, before I don't know, you go back like 40 years and it comes to like, how do we sort mail? Well, I don't know how long zip codes have been around, but zip codes were like introduced in like the 60s or something. And then people wrote zip codes on the letters, and then people would have to look at the envelope and they would read that with their eyes. And then they would say, okay, it's 99 something something. It's going to go over here. It's, some other number. It's going to go over here. And so these and then now we can like sort mail a lot faster because computers do it. But the hard part was, can the computers read handwritten zip codes and understand what these numbers are and then sort them accordingly? And so a lot of effort was put into being able to read handwritten digits. All right. And now this technology has gotten so good that you can just take a picture of your check and deposit it, and it will like know how much it goes. Or like, I don't know if you ever put like your handwritten checks into, like, who uses checks, but if you get a check, like maybe you go to the ATM machine and then you scan it and then it takes the money and stuff like that. And so that's cool, right? Okay, so anyway, this data set, they have 60,000 images in a training set, and every single image is 28 by 28 square. There's a number in the center, and it's been kind of processed so that it's perfect. Okay, but it's handwritten, and we're going to try to see if we can understand it. All right, and so I've put a link to this, and this will take you to kind of the official MNIST database. And you're going to want to do this. If you type in MNIST data set, there's going to be a lot of people who like copied this and like made little CSV files, make Excel files and things like that. Those are all, I would say, inferior copies of this thing, because basically the CSV files are just going to be just ridiculously huge and a little bit harder. And so you know, the only problem is you got to download this .gz file, and I don't know when the last time you used a .gz file, but probably not very commonly. And you got to un-gz it. If you have a zip program, you can probably right-click and un-gz, unzip the thing. You might have to download some kind of zip program like 7-zip or something, which is free, and your Macs can un-gz it also. But anyway, you un-gz that, you put it into a folder called MNIST somewhere in there, or wherever this, wherever you put this R script, you can modify this path to be whatever it is. Okay, but when you can kind of load this thing up, and I'll just do this here and there, and this kind of creates this little these functions, which are basically helper functions as far as loading the data goes, and showing the images. Okay, so this was written by Brendan O'Connor, so just want to give credit to the person who actually wrote the script over here. Okay, so over here, I'm going to go ahead and load up the MNIST data. So I have this already downloaded on my computer, and it's ready to go. Okay, and so I load up the data, and you know, it's a pretty big data set, and this is stored in there. Okay, and I just want to kind of take a look at, say, you know, one of the like maybe the first element. Okay, so I'm going to just set j equal to 1. We'll take a look, and inside the training data, which is a list, the first element in y is the label. And so this is what this training image has been labeled. It's labeled with the number 5, and correspondingly there's an image, which is a 28 by 28 pixel image, and it's stored as this kind of this vector. Okay, or I'm sorry, 28 by 28 vector, which is 28 times 28 is 784, I think, 784. And so this is a vector, and it just contains the numbers 0 for basically areas that are white, and 255 for areas that are black, okay, or like black ink. And so everything's kind of been scanned and kind of, you know, turned into grayscale. And so areas that are dark, you know, where the pen marking is, you know, that's 255 or some high number. And this is just a big vector of, you know, 784 values. And basically, this is the image, the 28 by 28. I want to play this little clip from 3 Blue 1 Brown, which shows basically what's happening. Okay, we have basically this 28 by 28 pixel image, and we turned it into this vector of length 784. Except in the 3 Blue 1 Brown video, the base color is black, and then the writing is in white. Okay, but it's pretty much the same thing. And as far as, and all of the numbers have been divided by 255. So basically it goes from 0 to 1 rather than 0 to 255. Okay, but it's the same kind of concept. And I just kind of want to play this tiny short little clip here.
For example, the network starts with a bunch of neurons corresponding to each of the 28 times 28 pixels of the input image, which is 784 neurons in total. Each one of these holds a number that represents the grayscale value of the corresponding pixel, ranging from 0 for black pixels up to 1 for white pixels. This number inside the neuron is called its activation. And the image you might have in mind here is that each neuron is lit up when its activation is a high number. So all of these 784 neurons make up the first layer of our network.
Okay, did you just see that quick little animation where basically all the rows of the image instead of being arranged into the square 28 by 28, just gets put into just one vector of 784, right?
The first
So this
layer of our network.
Okay, and so if you remember, when we created our neural network for our example, we had an input layer, we had a hidden layer, and an output layer. And in today's example, I'm going to have that same structure. We have an input layer with 784 nodes. We're going to have a hidden layer, and I think I've arbitrarily chosen 150 or something like that, hidden nodes in the hidden layer. And then we're going to have an output layer. The video in 3 blue, 1 brown is going to have 2 hidden layers, okay, and that's fine. But just in our example today, I'm going to just have 1 hidden layer.
Now jumping over to the last layer, this has 10 neurons, each representing one of the digits. The activation in these neurons, again, some number that's between 0 and 1, represents how much the system thinks that a given image corresponds with a given digit. There's also a couple layers in between called the hidden layers, which for the time being should just be a giant question mark for how on earth this process of recognizing digits is going to be handled. In this network, I chose 2 hidden layers, each one with 16 neurons. And admittedly, that's kind of an arbitrary choice. To be honest, I chose 2 layers based on how I want to motivate the structure in just a moment. And 16, well, that was just a nice number to fit on the screen. In practice, there is a lot of room for experiment with a specific structure here. The way the network operates, activations in one layer determine the activations of the next layer.
Okay. So anyway, he goes on to explain. I don't know if you've watched this video yet. It's very good. The entire series that Grant has put together on his channel is excellent, and I highly recommend it. But anyway, we're going to kind of do something similar, except our neural network. Oh, maybe I only put 30 in the hidden layer. I don't remember exactly. What did I write? Oh yeah, 30 in the hidden layer. Okay, so it's just arbitrary. It doesn't really matter. But this is basically the image that I'm drawing here. We've got 784 nodes in the input layer. I've got 30 nodes in the hidden layer, and I have 10 nodes in the output layer, right? And all of these are kind of interconnected and things like that. So 3 blue, 1 brown, there's 2 hidden layers, each with 16 nodes. I've just done 1 hidden layer with 30 nodes. And again, the exact structure is a little bit arbitrary. If you get into more advanced neural networks, you can read about just different kinds of neural network structures that exist and different things you can do. But we're just kind of playing around with the simplest of neural networks, okay? And again, all we're doing is just, you use neural network and layers and stuff, and it sounds fancy, but we're really just doing matrix multiplication, right? We just have these big matrices and we're just multiplying them together. All right, so one thing to note here, though, is that our output layer has 10 nodes. We have a node corresponding to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, okay? And you might wonder, and you might go like, well, why don't you just have 1 node and have it go from 0 through 9, or just be some kind of number? And the reason why is that if you think about digit recognition, is that it is not actually the image is not the digit that when we classify a digit, it's not a regression problem, okay? That if you misclassify a digit, you just got it wrong, right? If the true number is 9 and you guess that it's an 8, that's wrong. If the true number is 9 and you guess that it's a 1, that's wrong, okay? Whereas if you treated it like a regression problem, if you have 1 node and you treat it like a regression problem, then basically values that are close to it are less wrong than values that are far away. So if the true number is a 9 and you predict an 8, a regression problem says, oh, that's pretty close, that's pretty good. And if you guess it's a 1, you go, oh, that's bad, you're way off, okay? But that's not how it works when it comes for digit recognition. Like if you're writing down your phone number to somebody and you give it, and they can't read your number and they just have the wrong digit, it doesn't matter if it's close or way off. It's the wrong, you know, they're not going to call the right person. Okay. And so, so whether it's misclassify, if the misclassification is off by 1 or the misclassification is off by 10 and 9 or 8, whatever, it's wrong. Okay. And so in order to kind of show that categorical nature of the digit classification, we need 10 separate nodes. Okay, 1 node for each possible value. So it's basically digit classification is a categorical problem or a classification problem, and not one of regression. We're not trying to get values that are close but a little bit off. We're trying to get the correct category, right? And so what we're going to do is we're going to say if the correct answer is 9, then the bottom digit should be 1 and everything else should be 0. Okay, or the bottom node will be 1 and everything else will be 0. If the correct digit is 0, the top node will be a 1 and everything else will be a 0, and things like that. So that's how we're going to set up our data here. All right. So anyway, this is what the data looks like. This is a vector of 784 values. And most of these things are going to be 0 except where the numbers are, or where there's ink. All right, and we can kind of just take a look at some of the other digits here. So if I just want to kind of say, you know, what's the second case? It looks like that. What is the third case? That's a 4. Fourth is a 1. Fifth is a 9. Okay, and this is actually the image that appears in the 3 blue 1 brown image as well. Okay, so this is a 9 and things like that. Okay, and so we're going to take this this label, which is you know, shows up inside our training data as the number 9, and we want to vectorize it. We want to turn it into a bunch of 0s and 9s here. Okay. So I'm going to go ahead and create this function called Vectorize. And basically, this is going to create a vector of 10 zeros. And then whichever the position that has the value is going to get turned into a 1. Okay, so I'm going to go ahead and I'm going to just apply that to everything here. And so we can see as far as the 5th image goes, we have zeros for all of the other nodes, and then the last node is a 1. Okay, and then for the second image, which is a 0. Okay, if we take a look at the vectorized value for the second image, because it's a 0, the first node is a 1, and then all of the other nodes are zeros. Okay, so we're going to kind of convert all of these things into vectorized things. Oh, you know what? Before I forget, let me give you your view quiz answer. I'll just go ahead and give you your first 2, which are A and D, apple and dog. First view quiz answers today. First 2 of them are A as in apple and D as in dog. Okay, so we'll so yeah, this is so there's the image here. All right, and so now I'm going to go ahead and I'm going to just run the code for the neural network. Okay, and so one thing to note is that I have 60,000 images. I have 60,000 images in my training data. And so if I try to do my matrix operation with all kind of 60,000 images, it would, maybe I've got a decently fast computer, so it might be able to handle it, but it's a lot of computation for it to crunch, and it's gonna be hard. Okay, so what we're gonna do is we're gonna do what's called stochastic gradients descent. And what this will do, this stochastic just means, you know, there's randomness involved. And so rather than doing all 60,000 all at once, we're just going to select 10 rows at random. Okay, we're going to select 10 rows at random, and we're going to just basically create a much smaller matrix. So our first matrix, our input matrix will be n by 784, right? So I've got 10 10 rows, 784 columns, and then I'm going to multiply it by my first weight matrix, then do the activations, then we multiply by our second weight matrix, and then do our activations and to get our predicted values. And so basically we're going to find, we're going to use the gradient using just those 10 rows, all right? And that's going to just be a lot simpler for us to do. We'll take a small step, and then we're going to repeat the process. We're going to take another random 10 rows. We'll calculate the gradient using those 10 rows. We'll take a small step, and then we'll repeat, okay? And so this is just kind of a little bit, you know, it'll also get us downhill. It's just that, you know, in the beginning with all 60,000, if we use the full data set, we could find out exactly the direction that points north, points uphill, and we can go in the exact direction that points downhill, okay? When you pick 10 rows at random, you know, the direction that points uphill is going to be a little bit off, right? It's not going to be truly in the correct direction, but overall, it should be uphill overall. And if you go in the opposite direction, it should, in general, be downhill. Now, there might be a couple cases where you go in the wrong direction or something, but overall, you know, even a small sample like 10, overall, more often than not, will point you in the right direction. And so we're just going to do this, and this will just do, you know, we'll do 6,000 iterations of 10. And that means we'll go through all 60,000 images at least one time, or just one time. And that'll be good enough for us, okay? And we can see how we perform, okay? So I hope I don't know if I need to make my text bigger, but here is, I'm just taking the code, and this is pretty much the same code that showed up in lecture on Friday, okay? And so I have a function for the sigmoid activation function. I have a function written in R for the derivative of the sigmoid function, okay? And then I also have a function that's going to calculate the cost. The cost is going to be the difference between y and y hat, except this time we have a vector of 10 y values, right? You know, one for each node, and a vector of 10 y hat values, again, one for each node. And ideally what we want is we want our output vector to be, you know, mostly zeros, and one value that's going to be very close to one. So we want one value that's going to be like 0.999 for the correct digit, and everything else should be 0 or 0.001 or 0.01 or something very small. We want to have values that are very close to 0 for most of the nodes, and one node to be close to 1, okay? And so when we define our network, our input layer is going to have 784 nodes, and our output layer is going to have 10 nodes, one node for each digit. And then my hidden layer, I've just arbitrarily chosen 30 nodes in the hidden layer. And I think that's fine. Okay, so my first weight matrix is going to be 784 by 30. It's going to be a fairly large matrix, okay? And I'm going to just populate my first weight matrix. Okay, so I'm creating a weight matrix. I'm going to just create a whole bunch of random uniform values. So I say random uniform input layer by hidden layer. So 784 by 30, so that, you know, around, you know, 2,000 something values. Okay. And so I'm going to take random uniform values. Our unif produces a value between 0 and 1. And what I'm going to do is I'm just going to subtract 0.5, okay? And all that's going to do is that's going to just help me produce some negative values, right? So I'm going to have some, rather than getting all positive values between 0 and 1, I'm going to get some values between negative 0.5 and positive 0.5, right? And that just helps as far as like some initial values that, you know, could be a little bit better, okay? Number of rows is how many in my input layer, 784. Number of columns is 30 in my, how many nodes I have in my hidden layer. Okay, the second weight matrix is going to be 30 by 10. I've got 300 values in here. Again, some random uniform starting values, 30 rows, 10 in the output layer. Is that okay as far as the structure goes? Let me just kind of pull up the diagram that I have from the last lecture. So it's this same structure. It's just I've got 784 here, and I've got 30 here, and now I have 10. You know, the diagram from this is a better image. 784 here, 10 out here, and now, but I only have one hidden layer. Okay, and so as far as stochastic gradient descent goes, I'm going to just basically shuffle up my 60,000 rows, and I'm going to say, let's do 10 at a time. Okay, we're going to just take 10 at a time. I'm going to create a bunch of little batches of 10 randomly chosen rows. Okay, and this is the algorithm. Okay, so we're going to this is how we're going to train our neural network. Okay, I'm going to just select 10 rows using from the stochastic kind of the batch gradient descent. So we're going to take 10 rows, and whatever rows those are, that's going to form my training data X. And we're going to also take the labels on those 10 rows, and that's going to form my training labels Y. Okay, so here, this is my training data X, my training data Y. And this part will give me my predictions using my current values of W1 and W2. So I do forward feed. I do X times W1. So your input matrix times your first weight matrix. We're going to apply the sigmoid activation function to get A2. We're going to take the output of that and multiply it by our second weight matrix. So here's the, kind of the forward propagation. Okay, we're going to take the output and multiply it by our second weight matrix to get Z3, and then we're going to apply the sigmoid function to those outputs Z3 to get our YHats. Right, so that's just the forward feed part. And then we calculated, we went through all of the process on Friday to get our gradients, our DJ, DW, and things like that. So we calculate our gradients, and this is the solution that we came to. Okay, so we have delta 3 being y minus y hat, element-wise multiplication with f prime or sigmoid prime of z3, and that's my delta 3. And then dj dw2 is a2 transpose times delta 3, right? So we went through the process of getting all the math, and so we're just coding up this gradient here. Okay, so we have that, and then we do the same thing with the gradient for the second weight matrix. So the second weight matrix, I have a delta 2, which is basically delta 3 times W2 transpose, element-wise multiplication with sigmoid prime Z2. And then the gradient is dj dw1, which is going to be X transpose times delta 2. So this is just a matter of the hard part's the math, but once you get the math, entering it into code is rather straightforward. Now, if you look at this, you're like, how did you even get here, right? This seems a little bit, this crazy how we got this, but the math part, we've done it. I hope my Friday lecture kind of made sense. I hope these lecture notes are okay enough to get you to this point, to help you understand how we got this this expression in the first place. But now that we have this expression, we have the gradients. Okay, and then gradient descent is just a matter of taking your current values, your current weight value, and then calculating the gradient, and then taking a step in the opposite direction. So we're just taking our weight matrix and then subtracting off some scalar multiplied by our gradient. Okay, and then I do that for my first weight matrix and my second weight matrix, because they have basically each of those have different gradient values. And so I take W2 and I subtract off its gradient. I take W1 and subtract off its gradient. Is that okay as far as the implementation of this code, right? All right, and so again, it sounds fancy because we're using the word neural network, but really all that's happening is we're just doing matrix operations, one function with, the logistic function and things like that. Yeah, it was a lot of work getting these gradients, but these themselves are also just matrix operations. Okay, so I'm going to go ahead and run this, and this is going to run through 60,000 images. So it'll take like it'll take a moment, okay? But my computer's pretty fast, so I'll run it, and it's going through the 60,000 images. Okay, and now it's done, okay? Depending on your computer, it might take take a moment longer, okay? All right, so let's see how it performed, okay? And so now we're gonna go over to the test data, not the training data. So we had 60,000 images in the training data, and now we're gonna go to the test data. We have 10,000 images in the test data set, and we wanna see how well does it perform, okay? And so in order, one thing we did at the beginning was we took all of our values and we also scaled it by dividing everything by 255, okay? So that it's a value between 0 and 1. So we're going to take that for test data. Okay, so I'm going to take my test data, and what I want to do is I just want to go through, we're going to get all of the predictions. So we're going to just do forward feed. We're going to take our X test data, and we have the first weight matrix trained. We have the second weight matrix trained. And so this will give us our Y hats for all of our test data. Okay, so I'm going to just do forward feed. I'm going to say, take my input matrix X, multiply it by our first weight matrix to get our value Z2. Take our activation function, the sigmoid function, apply it to Z2 to get our activated values in the second layer. Take our activated values in our second layer, multiply it by our second weight matrix, which we have trained, to get our values Z3, apply the activation function Z3 to get Y hat. Okay, now what Y hat is, the dimensions of Y hat is, I've got 10,000 rows and I've got 10 columns, okay? And so if I just do head on Y underscore hat, okay, you know what, let me round this. So we're gonna round head Y hat. Let's round it to 4 decimal places. Okay, these are the outputs of Y hat. Okay, so Y hat, I've got 0.0001, 0.000, 000, and then I have a 0.9999 and a 0, and then I got a 10 to the negative 4. Okay, or 1 times 10 to the negative 4. Okay, so which one are we guessing? Well, this corresponds to this number here. And what digit is this? It's in the 8th column. So this is digit 7, because remember, this starts off at digit 0, and then the last column is digit 9. So I go 9, 8, 7. So this corresponds to digit 7. Okay, let's look at the next row. The next row, we're not so confident, actually. Okay, we've got something, 0.0037, 0.001. I've got a 0.6914. That's not quite 1. Okay, but this is the largest number, 0.6914. I've got a 0 over here, 0, 0, 0.0016, 0, 0, and 0. And so so basically this is it's gonna guess that it's a 2, right? So this is the largest value. Over here, I've got 0, I've got a 0.9998, 0.0002, a 0, 0, 0, 0, 8 times 10 to the negative 4, 0.004, 0.0008, 0.0002, and pretty much 0 over here. All right, so this one is going to get classified as a 1. Right? Is that okay? How this is going? All right, and so basically what I'm going to do is I ask the max column, which is going to just tell you, oh, the maximum column is the 8th column, the maximum column is the 3rd column, maximum column is the 2nd column, and then I'm going to subtract 1 just because this thing is 0 indexed, the columns are 0 indexed, and so my guesses will be this, right? And so if I just say, what are the first few values and guess, yeah, the first one is a 7, the next one is a 2, the next one is a 1, and so on and so forth. All right, so those are my guesses based on this. One thing I do want to point out is that these are not probabilities. These are just numbers that the neural network outputs. Sometimes we see like a number between 0 and 1, and we're tempted to say, oh, these are probabilities. These are not probabilities. Like if you take this row and you add it up, it's not going to sum to 1. Okay, you take this row and you sum it up, it's actually going to get bigger than 1. Okay, or this row, if you sum them, you're going to get a value bigger than 1, and things like that. These are not probabilities. It's just some number between 0 and 1 that the neural network the neural network saw the output, which is zeros and ones, and it's trying to get numbers close to the training data, which were zeros and ones. Okay, so it doesn't, neural network doesn't have a concept of probability. It's just saying, you know, in the training data, I saw you wanted me to give you zeros and ones, so I'm trying my best to give you something that looks like zeros and ones, and that's all it's doing. It's not, there's no concept of a probability here. Okay, so let's see how it performed. All right, so this first digit is supposed to be a 7, right? The first digit is supposed to be a 7. Let's go ahead and just take a look at what that digit looks like in the thing. So let's point that out. And indeed, that looks like a 7 to me. Okay. The second digit, it got classified as a 2. And if you remember, its classification for 2 wasn't super confident. It was a 0.6914. Let's go ahead and take a look at what it looks like. And yeah, it says, yeah, this is the thing. All right. So this is, it guesses a 2 here. Our next digit is supposed to be a 1. Let's just take a look at it. And yeah, that looks like a 1 to me. Okay. And our next digit is supposed to be a 0. And let's go ahead and take a look at what it is. And yeah, that's a 0. Okay. This is where you're supposed to be amazed. Or I don't know. This is supposed to be pretty cool, I think, right? All we did, like, we're now successfully able to kind of classify digits, right? I can, let's just try out a few more, right? The next one, it's supposed to be a 4, and let's just kind of take a look at what the, what the digit is. Yep, and that's a 4. And here, let me just, we'll just call some value P. All right, so let's just try the 100th image. Okay, its guess is a 9, and indeed that's a 9, right? Okay. All right, so let's see. Can we say that the number between 0 and 1 is the particular confidence percentage? It's not. Confidence percentage wouldn't be really the, I don't know. It's just a number that the network is outputting, kind of showing, you know, what the network is trying to predict. The network's trying to just produce outputs that match what the training data was, which was zeros and ones, and it's just trying to match that. And so the numbers that's closest to a 1 is going to be the one that it should be. How many layers do they use to classify the cats? Yeah, the one for the image net, the one that like won and beat the human performance, that one has like I think it has probably like 500 hidden layers and stuff. Okay. And so is it a question, is it important to know how the network arrived at the number? And the answer is no, we don't. Yeah, we're not trying to concern ourselves with how. We just want the predictive performance to be good. And all we did, again, the structure of our network is just, we've got some input. We have our case, we only have one hidden layer, and we have an output. And we said, you know, and what we needed to do is we needed to figure out all of the weights. There were so many weights for us to figure out. There was like, you know, 2,000 something weights between, you know, because we had 784 nodes here and we had 30 nodes here. So 784 by 30 is, you know, some big number. And we had to figure out all of those weights, and we trained those weights by using gradient descent, right? So we went through the process. So Friday was all about how do we figure out the gradient, okay? And now that we figured out the gradient, we're just going to say, okay, we're starting at this arbitrary location in n-dimensional space. N-dimensions, the number of values we need to kind of hone is, you know, on the order of like 2,700-ish, something around there, 20, let's say 2,500 values. So we're in this 2,500 dimensional space, and we want to get to the bottom of the hill, and the direction that we're going to travel in 2,000 dimensional space is determined by this gradient here, right? This gradient is this very high dimensional value, and that just points us kind of downhill. And so we did that. We run it over, you know, 60,000 images, and this is the results. Okay. So here, just to kind of evaluate the overall performance, I'm going to take the actual value and I'm going to compare it to what our guess is. This is what we call a confusion matrix, okay? And I'm going to go ahead and I'm going to just create a table out of it. All right, so this is our confusion matrix. And so when the actual value was a 0, it guessed 0 962 times. Occasionally, when the actual value was a 0, it guessed a 2. Occasionally, it guessed a 4 or a 5 or a 6. I can understand how a 0 could get mistaken for a 6. Sometimes it guessed a 7 or an 8, okay? When the actual value was a 1, it guessed a 1 1,113 times, and sometimes it got it wrong. Sometimes it guessed the 1 as an 8, okay? When it was a 2, it guessed 2 924 times. And basically, everything down this diagonal means it got it correct, and everything off diagonal are the times it made a mistake, okay? And so if I just take the diagonal and I divide by how many values we had total, we're achieving around 93% accuracy, 0.9287, which I think is pretty good, okay? Considering how simple our algorithm, our neural network is, okay? We had one input layer, one hidden layer. I mean, of course, we only have one input layer, but we only had one hidden layer with 30 nodes. And we're achieving around 93% accuracy as far as guessing the correct digit. Okay, and again, this is all just doing some matrix operations. It's nothing really, I don't think there's any like math here that was like super mysterious. Okay, admittedly, the work to get the gradients on Friday was a bit of work, but as you know, once you have this, the operations that are being done here is not like some mystery. Okay, and we're achieving around 93% accuracy, which I think is pretty good. Okay, and of course, you know, if you make a more advanced or more complicated network, you can probably get even better results. Right, and I just kind of want to take a look at some of the mistakes. Right, so which values didn't get correctly identified. So if we look at some of these, like 9010 is an image that was incorrectly identified. Image 116 was incorrectly identified. So let's just kind of take a look. So in the training data, the image is supposed to be a 7, okay? Our system guessed it was a 2. Let's go ahead and take a look at the digit. This is the digit that went into the system, okay? And so the correct label is a 7, and you go, oh yeah, I can understand that's a 7. But then our system thought it was a 2, and you go, it's all right, computer, you did your best, right? Like you feel like you understand why the computer mistook this for the number 2, okay? And you can take a look at some of these other things. So this image got mislabeled. The correct answer is a 4. Our computer thought it was a 6, and you're like, how does a 4 look like a 6? And you look at this and you go, oh, it kind of makes sense for like, how does a 4 look like a 6, right? And things like that, because again, this was, you know, one of the reasons why the data set is a favorite is that, you know, they took real handwritten samples and somebody like scanned them all and resized them to be exactly 28 by 28. That was a lot of manual labor going into this. But now that we have this very clean data set, we're able to, you know, so a lot of work on, you know, the advancement of neural networks was done using this handwritten data set. There's a whole bunch of different, you can see a whole bunch of different things. And so you have different classifiers, k-nearest neighbors, and things like that. And as far as neural networks, you know, they just talked about different what do you call it? Different systems that have been done, okay? And, you know, it's error performance and things like that. And so the error rate got, you know, kept getting better and better and better over time and things like that. So, you know, right now our simple neural network, we've got an error rate of around, you know, 7 or 8%. We got, you know, 92, 93% accuracy. And so we have an error rate of around 7%. But, you know, obviously other neural networks can do a lot better here. Okay. So anyway, I thought that was kind of neat as far as just showing how the neural network performs as far as taking some input image and producing a prediction from it. Okay, the code has all been posted online for you here, and you can kind of play around with it. You can also use this code as a use this code and also the code that I've put in the lecture notes as a bit of a starting point for your next homework assignment, which is going to be dealing with neural networks. But in your homework assignment, you're going to have to do a little bit of math work where you have to figure out the gradients for when we input biases into the neural network design. Okay, so that will be coming up. Don't worry, this stuff does not appear on the midterm exam for on Wednesday, maybe the second midterm exam, but as far as Wednesday goes, this stuff does not appear. All right, let me go ahead and give you your last view quiz answer for today. Last view quiz answer is E as in elephant. E as in elephant is your last view quiz answer for today. Okay, any questions or any comments you guys want to say before I let you guys go? Nope. All right. Well, we'll end here then, and have a good night, and we will see you guys on Wednesday for the exam. Oh, question. Do you about when the last lecture is that will be on the midterm? Oh, I don't remember what I was talking about. I don't know. I have a document on the midterm 1 topics, and this is pretty much what your midterm will look like. Okay, it'll look like this, and so if you study this, then you'll be good. Okay, 3.2 and on is on neural networks, and yeah, okay. So then 3.2 after that, not covered on this midterm because it's up through 3.1. Thank you. All right, good luck, and we'll see you guys on Wednesday.